Well, hello and welcome back to Engineering 202. I wanted to go over the sample exam number 2. You'll find this on the website. If you've happened onto this video from some other direction, I will put a link to the excuse me, a link to the website in the description of the video. Having said that, I would certainly recommend that you print out the sample exam without solutions and try it on your own. If you can print it out and knock it out in about an hour, I think you're in great shape. But I would highly recommend you trying it on your own first before you look at the solutions that are on the website and before you watch this video. But assuming that you've done that, you want to see me go through the solutions, we'll go ahead and get started then. I have printed these out. It's probably still a little small or blurry on the video. But remember that you've got the original on the website with the solution. So if we look at this problem here, problems 1, 2, and 3 are going to be based on this circuit, and we're told that the voltage across the load that's here, we've got 240 at 0 RMS, so 240 at 0 volts RMS. And we're told about load number 1 that it's 30 kilovolt amps. So immediately I recognize I'm given the hypotenuse of the power triangle, right? So I've got 30 kVA, kilovolt amps. If I was given watts, I'd be down here. If I was given VARs, I would be up there, the right triangle, with a 0.9 lagging power factor. So with a lagging power factor, I could say that the arc cosine, inverse cosine of 0.9, that turns out to be what, 25.84 degrees. So now I know what I know theta is right there, and with that theta, I could use that and figure out what the complex power was. And if we could say that S, the complex power, is equal to the voltage times the complex conjugate of the current, right? Or I could say that the complex conjugate of the current is equal to the complex power S divided by the voltage V. So this would turn out to be equal to, what would we have here? I'm going to take this thing, and I have 30 kilovolt amps. So I've got 30,000 at an angle of what, 25.8. 25.84, and so that's just using that, and then I have to divide this thing by the voltage, which is 240 at 0. Now, one thing, this is the conjugate, so if I want the actual current here, I'm going to have to put a negative sign there. That comes from the conjugate. So if I run through that, basically just 30,000 comes out to be 125 at an angle of, again, minus 25.84, and this would then be amps RMS. Okay, so that's how we could get that. Maybe I would be better off to say that this is I1, right? Because that's the current that we've got there. And does that make sense? If our voltage is at 0, this has to be lagging it, doesn't it? Because it looks like that we have a lagging power factor with that. Yeah, lagging power factor. So if I were to look at this on a phasor diagram, we've got the voltage here, and we would expect the current to be like that. So I think we can be pretty comfortable with that answer. Do we I1 125 at minus 25.84? Yep, looks like answer A. Well, current 2. what are we going to get for current number 2? Well, if I look at load number 2, we've got 40 kilowatts. So I do a very similar process here. I look at my power triangle, but this time at kilowatts, I know that I'm 40 kilowatts down there because I have volt amps, vars, and kilowatts. Then I've got the angle theta in there, which comes from the, again, lagging power factor. A little more common to have lagging because of all the inductance that we have in industrial settings. So I'm going to say that theta is equal to the inverse cosine of 0.795, which gives me 0.795, 37.34 degrees. So I know that angle there. Well, I'm going to go back to my old friend that power is equal to what? V RMS times I RMS times the power factor. If you want to be really fancy, you could say that this term here was apparent power. So apparent power times the power factor. And I'm going to rearrange that. I'm going to get my IRMS out of there and say that's equal to the power divided by V RMS times the power factor. So we have, what, 40,000 divided by VRMS 240, and the power factor 0.795. Okay, which turns out to be, let me double check that, yep, 209.64. And that's just the magnitude. Now I have to figure out the angle. So if I take this and I take this, I should be able to talk about what I2 is equal to. It's going to be equal to that 209.64, or maybe we'll just say 210. At an angle of what? Well, again, if I come up to my phasor diagram, this is lagging. So if the voltage is here with a 0 angle, that's that 240 at 0, I know the current has to be here, so I have to have some negative angle, don't I? So I would have minus 37.34, and that would be amps RMS. So that negative came from noting that it was lagging, that we had a lagging power factor. So be careful of that. Well, do I have that answer here? Let's see, 210 minus 37. Yep, right here. Answer C. Well, if we go on to then the third question. So the third question asks, what is Vs? What's that thing right there? Well, I know that this current here is going to be I1 plus I2, right? So I could say rather easily that this voltage Vs is equal to 240 at 0. I mean, we take this voltage here and essentially add the drop across there. So I'm going to take 240 at 0 and add to it the drop in the line, just to kind of lay out a roadmap of what we are doing. And so this would then be equal to 240 at 0 plus, how am I going to get the drop there? Well, if I just take the current, I1 plus I2, I've got both of those, and multiply it by the impedance. What's the impedance there? 0.1 plus j 0.1, 0.1 plus j 0.1. I should be good to go with that. So if I take I1 and I2, there's I1, and there is I2. And unfortunately, that's based on the previous answers. There's not much of a way around that on this problem, but let's take those. So we could say that this is 240, whoops, 240 at 0 plus, and then what do we have for I1? 125 at an angle of minus 25.8 plus, then I2 is 210 at an angle of minus 37.3. I'm going to add those together and multiply that by 0.1 plus j 0.1. So I think this whole thing here turns out to be 333 at minus 33.04. You probably want a calculator for that, because to do that by hand you'd have to convert these both to rectangular and add them together. So it'd be nice to throw that in your calculator, hit the add button, it would do that. Once you get that, you can multiply it by that and then add it to that, and it turns out to be equal to 286 at an angle of 1.95 volts RMS. So 286, 1.95, looks like we have answer D. So fairly straightforward, mainly just a exercise in working with complex numbers, circuit simplification, and so forth. Well, let's move on to problem number 4, or I guess rather questions 4 and 5. And a couple of things, we're going to look at the following circuit. Take the voltage at 60 and 250, so we have to be careful. Our omega now is 250. We're not in RMS anymore, so we need to remember that, not RMS, so keep track of that. And when we look at this, we've got a circuit here, and we'd like to find the value of the capacitor. We could put in, that would put the current I here in phase with the voltage source. This is really like lab number 3. I mean, sometimes it helps if you can liken it to something that you've done before and go through that. So we'll attack it much like you did laboratory number 3 or laboratory number 3's pre-calculation. So let's go ahead and do that. If I were to look at this here and put this into a phasor domain, I've got what? J times 40 milli is going to be 0.04 times omega. So this is J omega L, or I guess I've switched the L and the omega on you, haven't I? Okay, so what was omega? 250. And so that turns out to be equal to what? J10. That should be an easy number to work with. We've got 15 up there. We've got the capacitance here. I think I'll just call this X sub C, and we'll let the negative sign take care of itself later. So if I look then for the impedance here, the impedance of this whole thing, I could say that it was these two parallel branches, so it's product over sum. So I have 15 plus J10 okay, so there's 15 plus J10. So product, and then I need to multiply by this X sub C, there's the product, divided by the sum, which is going to be 15 plus J, and then I will have 10 plus X sub C. And again, I'm going to figure that when we make the substitution for X sub C, I'll put the negative sign in there. If you wanted to, you could put the negative sign on X sub C now. I've chosen not to. I will do that later. Well, what I'd like to really do is I'd like to figure out the angle for this. So if I look, the angle on this thing is going to be what? I could say theta sub z would be equal to, does this piece have an angle? Yeah, it sure does. So I'm going to say the arctangent of what? The imaginary portion over the real portion, so 10 over 15, and that really just comes from if we put these on a complex plane. There's the real, there's the imaginary. You would go out here at 15, and you'd come up here at 10, and you have this point And we're looking at that angle right there. Of course, the arctangent of 10 over 15. And then because I'm multiplying these, I'm going to add the angle, and this x sub c, because I'm going to put the negative sign in there later, it would have an angle of 90. If you chose to put the negative in now, you'd have a minus 90, but I'll put a positive 90 because I'm going to put the negative in later. And then because I'm dividing, how do we divide? When we divide, we subtract, right? Okay, this of course comes from multiply, and this comes from divide. So what do I have to subtract? The arctangent of 10 plus x sub c divided by 15, right? So this is what I would like to solve, and I know that if determine the value of the capacitance that will put the current in phase. If it's in phase, theta sub z is equal to 0, right? So when I put that equal to 0, I can solve for x sub c. And going through this, this is just a number. You could subtract it to the other side. That's a number. You could subtract it to the other side, multiply both sides by minus 1, and then take the tangent of both sides. So you'd end up with minus 1.5 is equal to 10 plus x sub c divided by 15. And that's just setting this equal to 0 and solving this equation. So if I solve this for x sub c turns out to be equal to minus 32.5. And that's that negative sign that I kept talking about. So there it is. And we know then that x sub c has to be equal to what? Minus 1 over omega c. That comes from minus j over omega c. I don't need the j in there, but I have minus 1 over omega c. Well, when I put this at 250, that's my omega. We've used that a couple times now. You can solve for c. C turns out to be equal to 123 microfarads. 10 to the minus 6, 123 microfarads. That's not a good answer there. That would be it. So answer D. And then using the value of capacitance from the above question, what is I of t? So we ask the question, what's that? So we take this answer, we plug this back in here, 123 microfarads, and we ask, what's that current? Well, to get that current, I really just have to find this impedance. I'm going to go back and pop that into that impedance. So maybe I will, let's see, we're at page, 3 here. So I'll grab a clean piece of paper. So we're back here. So I could say I'm going to go back and use this guy here with C equal to 123 microfarads. Then what is Z equal to? I'm going to have what? 15 plus J10 times x sub c. I guess I need to figure out x sub c, don't I? So x sub c would be equal to minus j divided by omega c, right? Which is minus j divided by 250 times c, which is 123 times 10 to the minus 6. Right? 123 times 10, yep. So this turns out to be equal to minus j 32.5. So with that, I put minus j 32.5 there. And then I'm going to divide by, 15 plus j. And then I'm going to have, let's see, I put the positive 10, and the minus 32.5 gives me a minus 22.5, right? Okay. Is that right? Double check that. Yeah. So when we run through this, again, you like using your calculator, make that a lot easier. Turns out to be 21.67 at an angle of 0. 21.67, who cares? I don't care about that. But the 0, I like that. That brings a smile to my face because I've got the impedance in here, so this should be in phase. The only thing else I have to add is this resistance, and that's not going to change the angle at all. Okay, so that's really good news. So now I can say that this I can say that, going back and using Ohm's law, I can say that I is equal to the voltage divided by the impedance. And maybe we'd better make a big deal. This is total, right? Total impedance. So what do we say? This is 60 at 30, isn't it? Is that what that is? Yep, 60 at 30. So I have 60 at 30, and then I'm going to divide this by 21.67 at 0. And then because this is total, I have to add this thing in, right? Plus 8. And again, you'll be glad you have your calculator because you got a polar and a rectangular. You add those together, and when you get done with this, that turns out to be 2 at an angle of 30. So that's the current versus the voltage. That is what? That was 60 at 30. They're in phase. So again, we can start to have a lot of confidence with our first answer. They're in phase. Now what were we looking for? We're looking for the current. Well, I have the current in phasor domain, but here I have it in time domain. It looks like my answers are in time domain, so I better put that in there. I could say then, so in the time domain, I would have 2 times, we're going to write it in terms of cosine. What was our omega? 250 t plus 30, and that'll be amps. Certainly not amps RMS. So do we have that answer? We've got 2 cosine 250 plus 30. It looks like answer A, doesn't it? Good. So a good solid problem. Again, like lab number 3, or maybe I should say the pre-lab. Those calculations. So again, if you just kind of faked your way through the lab, go back and look at that. That becomes important as you go on. Well, I got question 5 taken care of. Moving on to questions 6, 7, and 8. Give us page 5 then. We have a positive, ABC. So this is 3-phase. It's positive. Remember with 3-phase that it's always RMS unless told otherwise. So some things we want to think about. We've got a Y-connected source. So we have a Y-connected source that supplies a balanced delta load. Okay, so a Y feeding a delta. The impedance per phase of the delta is what? 10 plus J8 ohms. So impedance per phase, so that'll be ohms per phase. The line impedance is 0. Okay, so we don't have any drop in the line. In the A phase, the line current in the A phase is known as that. Okay. So let me build my single phase equivalent circuit. So to do that, I need to figure out, I need to convert this delta, convert to a Y. And I do that by saying that Z sub Y would be equal to Z sub delta divided by 3. So I have 10 plus J8 divided by 3, which gives me 3.33 plus J 2.67 ohms per phase in the Y. Okay, so I can come up with this single phase equivalent circuit. It's going to look something like this. I've got my source, and then I don't have any drop in the line, and then I can have this impedance here of 3.33 plus J 2.67, and it goes back around here. And I'm going to say that this is little a and little n and big N and big A. And we're told what? That AA, yeah, we're told this current up here is equal to that thing, right? I won't bother rewriting it. It's that thing. Now the one thing that we have to be careful of is this is a model, okay? Because it's really a delta. In real life it's a delta, but I've modeled it like that to make my calculation and thinking about it a little bit easier. So let's see if we can get through this. What is the phase voltage VAN at the load? Yeah, this is a little bit confusing. The phase voltage VAN, should we have said, maybe we got a bad test question here. Should we have said V capital A capital N? Because usually we have capital letters at the load, right? But since we don't have any drop in the line, it should be the same. So that would be a kind of a confusing question if I had a line impedance. Then the voltage here with respect to there would not be the same as the voltage here with respect to there. But since I don't have any impedance in the line, these two are equal. Okay, so with that, we can say we're really looking for this VAN, which we already said was equal to little a little n. Could I do that? Yeah, I should be able to do that pretty easily. VAN would be equal to, just going to take current 28.1 at an angle of minus 28.66, minus 28.66, and I'm going to multiply that by the impedance, 3.33 plus J 2.67, which gives me then, double check all this, yep, 119.94 at an angle of 10.06. So I think I could probably say, what, 120 at about 10? Probably be a safe bet. 120 at, make sure I answer the right question, 120 at 10. So I think we're good there. Because this would be the same as V little a little n, wouldn't it? So what is the line voltage AB at the load? Okay, the line voltage is going to be not from A to the neutral, but from A to B. So I could say that VAB would be equal to this answer here, 120 times the square root of 3. So I take that and I multiply it by the square root of 3, and then I take the angle there, and because it is positive phase sequence A, B, C, I'm going to do what to it? Add 30 degrees. So with that, I come up with what? 208 at an angle of 40 volts RMS. So 208 at 40, we've got answer D. And then finally 8, what is the magnitude of the current in the load? Well, before we say that it's equal to this, and this must be some sort of a trick question and we're tempted to answer here, we've got to remember, this is not what the load is. This is a model of the load, isn't it? So I want to go in and I want to actually find, if I look at this, remember we've got this delta here, don't we? And I've got I've got this current here, isn't that? That's I little a big A. But I really would like to find the current in here. What is the current, the magnitude of the current in the load, in the delta load? So how do I get that? Well, so for the, separate this off, see if I can get this all on one page. For the delta load, I could do this a couple of different ways. I could say that it was simply this number here that I was tempted to use, this value up here, 28.10. I'd have to divide that by the square root of 3, and then as far as the angle goes, minus 28.66. What would I have to do to that? I'd have to add 30 because it's positive phase sequence, and that turns out to be equal to 16.2. Should be less. Good. 16.2 at 1.34. Do I have that answer? Yeah, right there, answer C. Now, if you're not comfortable with that, and it's sometimes not obvious, sometimes the square root of 3 is fairly easy, but whether you subtract 30 or add 30, that's always a little harder, and probably, hopefully on your note card, you've got some examples of that from lecture. We went through that in lecture. What would be another easy way to prove this to yourself? Well, we know that the voltage across here is what? We just answered that, didn't we? So that's 208 at 40. So 208 at 40. And do I know the impedance here? Yeah, that was the original impedance that was given right there. So I could find this current. I could say, or we could take what? We could take the voltage and we could divide by the impedance. So what is the voltage? 208 at 40. And then if I divide by this 10 plus J8, because I've got the line-to-line voltage there, and then I have this impedance that's right there. And when you go through that, you get the 16.24 at an angle of 1.34. Okay, so I like that a little better. That makes me a little more comfortable. I don't have to remember, do I divide by root 3 or multiply by root 3, add 30, subtract 30. So if I can find a method like this, I'm always a little happier with it. But you could do that too, and if you get in this business, you're going to almost instinctively know whether you add or subtract that 30 and the root 3. But if you're wanting verification of your answer, there's a good one there. So we've got 8 done. Let's move on. Double check that, 16.2. Okay, so we wrap up with the last question here, which use the following descriptions for 9 and 10. A three-phase circuit has 2 parallel balanced delta loads. Okay, so schematically, I have something like this. There's one of them. And then I come in and I put another in here. And when we have three-phase loads, they're almost always in parallel, because if they were in series and you turned off one machine or one industry, you would end up turning off all of them. So we make that connection there. We make this connection here, and then this one we have to come over here and jump around that and go up to that. Okay, so we've got 5 ohms per phase here, and we've got 20 ohms per phase there. And the line voltage, so the voltage across the line, is 480, which is also a common value, 480. So we'd like to find the magnitude of the total line current. So what we could do is we could put this thing, we could put these two sources together and say that this really looks like one delta. like this, right? And each one of these would really be just 5 ohms in parallel with 20 ohms. So we go product over sum. 5 times 20 divided by 25 gives me, what, 4? 4 ohms now per phase. So I got 4 ohms per phase. And we're told that this is, again, 480. So I could say then that the current, I, is going to be equal to 480 divided by 4, which gives me 120 amps RMS. Okay, that's the magnitude. And where is that? That would be right in here, wouldn't it? Yeah, I mean, we've got the voltage across there, and we've got 4 ohms. This is 4 ohms, so that's the current that we've got in there. And what do we want? Line current. Okay, so this is what I'm looking for, isn't it? So what I can do is I can take this and say that the line is going to be the square root of 3 times that 120, which gives me 208 amps RMS. And I don't have to worry about the 30. We weren't given any angles. We're just working in magnitude here. So the answer is 208. Unfortunately, the 120 was sitting there waiting for us, so it didn't fall into that trap. That's good. Then the last question, find the magnitude of the phase current in the 20 ohm phase of the delta load. So we're looking for the phase current. So we're looking for one of these currents down through there, right? Okay. So that would really just be as easy as, what's the voltage across there? That's 480, isn't it? Things in parallel have the same voltage, so I take 480 and I divide by volts divided by ohms, gives me 24 amps. Is that right? I think so. Well, that seems like a long ways from 120, right? Well, so what if I go over here and I ask the same thing of this 5 ohms? What's that current there? So I take 480 volts and I divide by now 5 ohms. What's that give me? 96? Is that right? Yeah, 96. And now when I add those together, I get the 120, and I have a lot of confidence in that answer, and I have more confidence in that answer right there. Okay, so we would have 24 or B. So this gives you hopefully a good set of problems to look at, defines the material pretty well that you would be expected to know for the exam. Again, I encourage you to sit down and make sure that you're comfortable with these problems, work them multiple ways, and get yourself ready for the examination. Well, I will leave you with that, and take care until then. Thank you for watching.